Welcome back, everyone. We're diving right into Lesson 9 of our GD&T Master Course. Today, it's all about circularity, or roundness, and how the ASME standards have evolved to save us from catastrophic part failure. Think about this for a second. You've got a precision shaft. You grab your calipers, measure the diameter, and boom, it's perfectly within spec. But then you throw it into the machine, and the thing vibrates like absolutely crazy. Why? Well, because diameter alone is never going to guarantee proper rotational performance if the part is out of round. Form matters literally just as much as size, and that's exactly what we're unpacking today. To see why getting this stuff right is so crucial, take a look at this quote from an engineering forum. "Putting datums on center lines, that is my pet peeve." I know, it sounds like a tiny little detail, right? But applying datums to circularity is a massive, incredibly common mistake that causes just total frustration out on the shop floor. Circularity actually operates completely independently of datums. When drafting errors like this creep into a blueprint, you end up getting 5 totally different interpretations from the client, the machinist, and the vendor. And look, we want zero ambiguity here.
So here's our quick agenda for today. 1. Common GD&T drafting errors. 2. Form controls and circularity. 3. Location controls and virtual conditions. 4. Runout, measuring the wobble. 5. The 2018 ASME updates. And 6. Eliminating drawing ambiguity.
Section 1. Common GD&T drafting errors. Now, according to industry data from Sigmatrix, the incorrect use of feature control frames is just a huge problem. These frames are what define the type, shape, location, and orientation of your tolerance zone. But, designers often make these really simple mistakes, missing symbols, misordered modifiers, or maybe using incorrect datum references. And these aren't just harmless typos. Misordered modifiers or bad datum references will absolutely ruin your roundness controls and completely alter how the part is interpreted. That leads to a ton of vendor confusion, those endless back-and-forth email chains, and ultimately your parts ending up straight in the scrap bin.
Section 2. Form controls and circularity.
So, form controls dictate the final physical shape of your custom components, basically limiting just how much a part can structurally deviate. The 4 main controls we look at are straightness, which ensures uniformity across surfaces or axes, flatness, which limits the difference between the highest and lowest points, circularity, which controls that roundness parameter, and cylindricity, which actually combines straightness and roundness together. Mastering these is absolutely critical for functional success, like making sure hydraulic pistons seal up perfectly or that mating surfaces sit nice and flush. But today, we are laser-focused on circularity.
Okay, so circularity is a 2D tolerance, and the standard defines it in a really elegant way, actually. Think of it simply as straightness that has been bent into a circle. It defines exactly how close your circumference needs to be to a perfect mathematically ideal circle. In practice, the tolerance zone is made up of 2 concentric circles. The radial separation between those 2 boundaries, well, that's your tolerance, and the entire circular profile has to remain trapped right inside that zone. Crucially, and remember this tolerance zone floats freely. It doesn't reference any external datum. This independence is exactly what keeps your feature from ending up too square, oblong, or, shaped like a potato.
Now, a super common mistake we see is people confusing circularity with cylindricity. Look, circularity is strictly a 2D tolerance evaluating individual cross-sections. You basically slice the part conceptually and just look at that one specific slice. Cylindricity, on the other hand, is a 3D tolerance. It measures straightness and roundness along the entire length of the part, all at the same time. To give you an example, a simple 2D circularity check is usually plenty for a static seal surface. But full 3D cylindricity, that might be required for something like a high-speed bearing journal that's rotating under heavy service loads. The takeaway here? Please don't over-specify if a simple 2D check gets the job done.
Section 3. Location controls and virtual conditions.
Let's talk about virtual condition. This represents the absolute worst-case allowable limit to guarantee that a pin will actually fit into a mating hole. Let's step through the math here. It's pretty straightforward. For an external feature, like a pin or a precision shaft, the virtual condition is the maximum material condition, which is the largest allowable size, plus the geometric tolerance. For an internal feature, like a drilled hole, it's the maximum material condition, meaning the smallest allowable hole size, minus the geometric tolerance.
So, let's say your pin's maximum size is 25 millimeters, and you have a straightness tolerance of 0.1 millimeters. That means your virtual condition is exactly 25.1 millimeters. If the part has any shape variations at all, like poor straightness or bad roundness, that cause the cylinder surface to bulge outside that 25.1 millimeter virtual boundary, it simply isn't going to assemble. Think about it.
Even if your calipers are telling you the diameter is totally fine, an out-of-round, potato-shaped shaft is going to push right past that boundary and fail assembly.
Section 4. Runout. Measuring the wobble.
Runout is essentially the ultimate test for wobble. It measures the deviation limits of a circular feature's ideal position when you rotate the part a full 360 degrees. To actually measure this out on the shop floor, you typically place the part in a precision spindle system or maybe some V-blocks, and you run a dial indicator right against the surface. As the part turns, that dial indicator catches the exact variation. And let me tell you, just one single deviating feature outside the tolerance can completely throw off the entire assembly and make the whole fabricated part completely unusable.
Just like circularity and cylindricity, runout comes in two flavors. Circular runout is your 2D measurement of deviation at an individual cross-section. Total runout is the 3D version, measuring across entire surfaces. When you're looking at these tolerances, you really have to consider the manufacturing realities. Things like turning or grinding operations can very easily introduce 2D or 3D variations. Tool wear, machine vibration, or even material distortion. Those are exactly the things causing the variation you eventually see popping up on that dial indicator.
Section 5. The 2018 ASME Updates.
The ASME Y14.5-2018 standard brought some pretty dramatic changes to the field. It clarified datum stabilization protocols, it added much-needed guidance for applying GD&T directly to 3D CAD solid models, and it completely banned two legacy location controls, symmetry and concentricity. Honestly, this is a massive win for basic form controls. Because these highly complex, confusing controls are finally gone, mastering our foundational forms like circularity is literally more important than ever.
Let me explain why they did this. Under the old 2009 standards, concentricity meant that the median points of all diametrically opposed elements of a surface had to fall perfectly within a tolerance zone. Let me tell you, finding these so-called derived median points on a real-world, irregular physical part is incredibly confusing. It's notoriously hard to measure, and it requires highly expensive CMM equipment. It's a total headache, and that is exactly why the committee just scrapped it entirely.
So the standard now makes it very clear. Position and runout are vastly better, far more cost-effective options for defining rotating features. If you're drafting a new part today, you really should just default to position and runout. In a lot of cases, simply checking basic circularity right alongside position achieves the exact same functional goal, but without forcing your quality department into an incredibly expensive, time-consuming measurement nightmare.
Section 6. Eliminating drawing ambiguity.
This concept is exactly where understanding circularity versus basic size control becomes so critical. Look, a caliper only measures a 2-point size, the diameter. It absolutely does not measure form or circularity. A feature can have a perfectly acceptable diameter but still completely fail a circularity check. For instance, bad centerless grinding can create this lobed, almost tri-oval shape. That shape will actually read perfectly in spec on a digital caliper, but it's functionally disastrous. Poor understanding of GD&T translates directly to wasted metal and wasted time on the floor.
As a designer, you absolutely must avoid the super common mistake of relying on ambiguous dimensions. Think about the old school plus or minus dimension for a radius. It's just highly ambiguous. I mean, where exactly is the center? What if the curve is totally irregular? Compare that to the modern unambiguous method that uses a basic dimension paired with a surface profile control. You need to be incredibly cautious about slipping back into those outdated drafting habits that leave things open to interpretation.
When you use a proper profile control, it creates a rigorously defined tolerance zone that is bounded by a minimum radius and a maximum radius. The actual physical contour of the part has to stay safely trapped right between those two boundaries. There is literally zero room for interpretation here. The machinist knows exactly what is required, and the inspector knows exactly how to verify it. Everyone is on the exact same page. So I'm going to leave you with this question to think about today. Are your current blueprints relying on outdated, ambiguous symbols that are quietly costing your shop time, money, and rejected parts? Really understanding controls like circularity and adopting the latest ASME standards is exactly how you fix that. Take these concepts back to your CAD files and start applying them right away. Next lesson, cylindricity, controlling the entire cylindrical surface.